Hello, my name is Mike Shutton. Today I would like to analyze an interesting RLC circuit, and that circuit is shown on the top of the page. And what I want to do is I want to measure the input impedance looking into this RLC circuit. And I'm going to have a couple of constraints on this problem. The first of which is going to be we're going to set these two resistors to be the same value or equal, and we're going to do a Laplace domain analysis to calculate the impedance. Now, anytime I have an RLC circuit, one of the characteristics I talk about is the resonant frequency. And one way of defining a resonant frequency is the frequency where the impedance of an RLC circuit goes resistive. And by that definition, I'm going to show that this circuit, with the constraints that I present, is going to be resonant at all frequencies. So we have this series R plus SL leg in parallel with this R plus 1 over SC leg. So we have an impedance shown like so. Now I can multiply out the numerator, and I get this equation shown over here. Now we can show that for the equal value resistance condition that we put in, the characteristic impedance of this circuit is square root of L over C. And the second constraint I'm going to put on the problem is I'm going to set these resistor values to be equal to that characteristic impedance, where R equals square root of L over C. Or I can say R squared equals L over C. Now notice I've got this L over C term here, so I can replace that with R squared. And that gives me the input impedance shown here. Now I can factor out an R term from the numerator. I get R times this term in the numerator divided by this term. Notice that the term in the numerator and this term in the denominator are equal, so I can cancel them out. And the impedance that I see is purely resistive, and it's equal to the value of this resistor R. Now let's just quickly analyze this circuit at a couple of boundary conditions. At low frequency, or DC, the inductor becomes a short circuit, and the capacitor becomes an open circuit. So the impedance becomes a resistor. At very high frequencies, the capacitor becomes a short circuit, and the inductor becomes an open circuit. So again, the impedance that we see, again, looks like a resistor. So for this circuit at low frequency, high frequency, and all intermediate frequencies, the input impedance looks like it's resistive, and it looks like it's the value of this R. Now I want to show a SPICE simulation of this RLC circuit. So I have the RLC circuit to the right, and in this particular case, I've chosen the resistor values to be 100 ohms. My inductance is 1 millihenry. My capacitance is 0.1 microfarad. So this has the characteristic impedance of 100 ohms. So again, that's the value that I've chosen for these resistors. To measure the input impedance, I'm doing it with an AC analysis. So I've got an AC voltage source. I'm measuring the magnitude of this voltage source divided by this current, and that will give me the input impedance seen from this circuit. So if we run the impedance analysis, I've shown it here. We're measuring over a frequency range of 100 hertz to 1 megahertz. Now notice the greatly expanded scale. I'm going from 99.8 ohms to 100.2 ohms. And you can see my impedance is basically flat over that entire frequency range of 100 ohms. My phase shift I'm plotting over here from minus 0.2 degrees to plus 0.1 degree. And you can see my phase shift is very flat, around zero. So that's the characteristic of a resistor. So at all frequencies, this circuit is looking like a 100 ohm resistor. Now, let's just do a quick change here. Let's make this capacitor, or this resistor in series with the capacitor, let's make that very large. So we'd just be measuring the impedance of this RL circuit. So we run the simulation, and we may expand that. As I stated, at low frequencies, that has an impedance of 100 ohms. It's going from 100 to 10,000 ohms. Again, my frequency range is staying the same. And I'm plotting the impedance here. And let's find the frequency. We're at 45 degrees of phase shift. There we are right there, 45 degrees of phase shift, 15.9 kilohertz. So at 15.9 kilohertz, that's where the real and imaginary component impedances are equal, or it's a 3 dB point. So you can see at 15.9 kilohertz and above, it starts acting predominantly inductive. And I have that 45 degrees of phase shift. Okay, let's change that around. And let's make it so just the capacitor leg is in the circuit. So we'll put that back to 100 ohms. And we'll make this an open circuit. So now I'm looking at the impedance of just this capacitive leg. If I run the impedance again, you can see, again, over the frequency range of 100 hertz to 1 megahertz at very high frequencies, we're going to 100 ohms. And at 15.9 kilohertz, that's going to be where we get our 45 degrees of phase shift again. So it's acting like a capacitance until at higher frequencies, it again acts like a 100 ohm resistor. For the measurement, I will be using a Bodhi 100 box from Omicron Labs, which is a very powerful low-cost network analyzer, and I will be using it as an impedance analyzer. And you also see a custom impedance measurement box which I constructed, which is similar to an impedance box that Omicron Labs sells. However, this box allows me to use a custom test fixture, and it also allows me to put multiple circuits in parallel. On the page, you see two circuits. On the right is an inductor with a value of about 26.5 millihenries and a series resistance of approximately 74 ohms. On the left, you see a test board, and on that test board is mounted a series RC circuit. The resistor is 75 ohms to try to match the 74 ohms of the inductor. And the capacitance, it would be selected to be L over R squared, or approximately 4.7 microfarads. I'm now going to do an impedance measurement. So in the impedance measurement box, I have the inductor. So we're measuring the equivalent RL circuit of that component on the screen. So on this screen, the black is the impedance, which we're measuring between 10 ohms and 6 megohms. And we're measuring over a frequency range of 20 hertz to 50 megahertz. The blue line is the phase, and we're measuring that between minus 100 degrees and plus 100 degrees. So you can, I've got the cursor here set at about 22 hertz, and you can see the resistance is about 74 ohms. Now if we find where the time constant is, the L over R time constant, that's where we have 45 degrees of phase shift. And in this particular case, that's happening at 439 hertz. So with these impedances, that works out to about a 26.5 millihenry inductor. Now let me change the inductor and replace it with the series RC circuit on my test board. So now we have the 75 ohms and the 4.7 microfarad capacitor in series, and we are now going to measure the impedance of that. And as you can see, the impedance is falling, and then when we get to a high enough frequency, the impedance is staying at about 75 ohms. And if we find where the time constant is, again, I'll set it for minus 45 degrees. You can see for this RC, it's at about 419 hertz. So I didn't match the time constants that great, but they're not too far off. So what I'm going to do is I'm going to take that test board that has the series RC, and I'm going to add in parallel the inductor, which is the series RL circuit, in parallel with the series RC of the capacitor. So there we have it. We'll run the impedance again. And notice what happens. My impedance is actually quite flat. So here's my impedance. My impedance is, so if we measure the value here, it's around 75 ohms. The impedance is quite flat. My phase is pretty flat, around 0 degrees. Let's change the scale here. Let's go from, instead of going from 100 degrees to minus 100 degrees, let's go 10 degrees to minus 10 degrees, and let's go 10 ohms to 100 ohms. So we can see this on a greatly expanded scale. So if I find where my phase is off by the largest amount here, and this is where my phase is off by the largest amount here, we're off by about 0.85 degrees, which isn't bad considering I really didn't do much of anything to try and match these RCs and L over R time constants that accurately. And as you can see, when I go up, I'm at about 75 ohms. And we got our 74 ohms of our inductor, and we've got a maximum value off at about a little more than 76 ohms, which isn't bad. And now one might think and say, why is it at high frequencies where my inductor is above his self-resonant frequency, why is this impedance still saying so well at 75 ohms? And the reason is my inductor, my series RL circuit, is still acting like many thousands of ohms even by the time I'm at 50 megahertz. And my RC circuit is acting like a pretty good 75 ohms. So I put those two in parallel, and that still acts like pretty close to 75 ohms. So this circuit works very well over a very wide frequency range.